very much. Our next speaker will be Aaron Poole, who will talk about charges in asymptotically locally de Sitter spaces. So please go ahead.
Okay, thank you very much, Julio. And thank you very much to the organizers for inviting me to give a talk at this meeting. I've really been enjoying it so far, learning a lot of new stuff. So hopefully I can add to that with this topic, charges in asymptotically locally DS spacetime. Now, this is work that I'm doing in Southampton in collaboration with Kostas Skenderis and Marika Taylor. It should be out on the archive reasonably soon in a sort of short letter format, which will discuss many of the main results that I'm going to chat to you guys about today. Okay, so if I can get it to move. So first of all, a little motivation for why one wants to look at this sort of topic. And the main one really is that of gravitational waves. Now, I probably don't really need to remind you all that gravitational waves have been detected by the LIGO collaboration, in the following scenario where one has two black holes or neutron stars, or even one of each, that in spiral and collide with one another. And in doing so, they give off gravitational waves, which we're able to detect using these Michelson-Morley type interferometers on the Earth. Now, I've cited the original sort of LIGO detection back in 2015, but now with the increased precision of the detectors, we're able to find, sort of the order of multiple detections a day. And so this opens a sort of new window, the universe of gravitational wave astronomy. So we can really get a good handle on sort of what kind of black holes and neutron star binaries are out there. So that's kind of an astrophysical motivation, but mathematically speaking, we really understand gravitational waves in something known as asymptotically flat spacetimes. So these are those with, if you think about the perspective of general relativity, these are those with a vanishing cosmological constant, so lambda equals 0. And much of this work was done sort of back in the late 50s, early 60s, by Troutman, famous papers by Bondi, Metzner, and Sachs, and also by Penrose. And something in common with all these pieces of work is that they identify a quantity which is positive, but monotonically decreasing as gravitational waves leave the system. So this is often referred to as the Bondi mass. So the debate is following kind of evolution equation. So as the U is the retarded time of the system, as U increases, this derivative is explicitly negative. So you can see here it's an integral of a squared quantity, so something positive with a negative factor at the front. And what this really measures is the mass lost by sort of the black hole system, if you like, as the gravitational waves leave the system and travel out to infinity. So this is sort of one of the principal early arguments in formalizing gravitational waves. Is not a coordinate artifact, but really something built into the nonlinear theory of GR. Okay, so gravitational waves, that's great. And we understand them well in lambda equals 0 spacetimes. But as it turns out, we're not ourselves in a lambda equals 0 spacetime. So again, as I'm sure you will know, the universe is now in a period of accelerated expansion. So in this kind of cartoon of the universe, we're sort of sitting around the lip of the sort of cup of the universe, if you like. And well, this expansion is driven by something mysterious known as dark energy. But in terms of general relativity, this is very well modeled with our universe having a positive cosmological constant. So instead of being asymptotically flat, we're in something called an asymptotically locally de Sitter spacetime. So that kind of leads us to sort of, putting these two questions together to form this goal of trying to develop a framework for gravitational radiation when the cosmological constant is positive. So this is not really just work that sort of I'm looking at alone, but there are many contemporary authors all using slightly different techniques to try and address this problem. So I've just cited a bunch of them here. So you can sort of see that, some Aninios and Strominger, etc., compare, perhaps coming at this from the high energy community perspective, but there are also people sort of perhaps more in mathematical relativity like Krushel, or gravitational physics like Ashtekar. So there are certainly ideas from different disciplines coming into this this puzzle. Okay, so so that's kind of the broad motivation. So I just sort of like to give an introduction to de Sitter spacetimes and their asymptotics. So first of all, let's just kick off with the basic pure de Sitter spacetime. I should mention we'll always be in 4 spacetime dimensions here. So pure de Sitter is the maximally symmetric solution to the Einstein equations when lambda is positive. So by maximally symmetric, I mean, well, possesses the greatest possible number of Killing vectors, the most symmetry. And so, of course, when one writes down the Einstein equations, you put in the cosmological constant, which one can express as something manifestly positive in the following way, as 3 over L squared, where L is a quantity known as the de Sitter radius of the solution. So what can we quickly infer about these type of solutions just from looking at the basic field equations themselves? Well, by taking the trace through all of this, one sees that these are solutions of constant positive scalar curvature. So that's this equation here. And geometrically, we can sort of visualize these as 4-dimensional manifolds embedded in 5-dimensional Minkowski space. So these are actually homeomorphic to hyperboloids, so R times a 3-sphere. So if this is the metric of the 5-dimensional Minkowski space, then the 4-dimensional de Sitter space that we're interested in takes the following form inside this Minkowski space. And this picture here is just obviously a lower dimensional. This is really a R times S1 embedded in R3, but you can imagine the same sort of construction of the hyperboloid embedding in the higher dimensional Minkowski space. Okay, so that's sort of the general introduction, but what about putting some coordinates on this de Sitter space? Well, a particularly nice set of coordinates are these global ones given by this time tau, and then there are 3 angular coordinates, chi, theta, and phi. And hopefully this form of the metric makes it quite clear to you where this R times S3 comes from. So you sort of have this real line sitting in the time part, and then there's the metric of the 3-sphere sitting here, multiplied by this conformal factor, cosh squared tau over L. If I could, can I jump back? I can jump back. So if you remember this sort of minimal radius sphere, the center of the diagram, this could also be thought of as the tau equals 0 sphere in these coordinates. So yeah, as I mentioned, the constant tau hypersurface are just S3s with this radius. So these are just some general coordinates that one can use to look at de Sitter, but we'll also be interested in the causal structure, and this is going to kind of be a key point that I'll keep coming back to throughout this talk. And so when one's interested in the causal structure of a spacetime, you tend to look at the Penrose diagram. So this involves performing some coordinate transformation to a conformally related spacetime, where the infinities of the original spacetime are now brought into finite affine parameter distance. This is sort of in order to be able to plot this, without having to reach to infinity. And when one plots these Penrose diagrams, you also suppress 2 of the angles. So you can imagine suppressing the theta phi directions in this picture, such that every point in the diagram now represents a 2-sphere. So because this is a conformally related space, it has the same causal properties, and in particular, the null geodesics of the space-time don't change, and they travel at 45 degrees to the horizontal in this picture. So what do we get? We just get a square, basically, probably something many of you are familiar with. But the key point I want to emphasize is that the infinity of the original de Sitter space is now mapped into 2 disjoint space-like components. So one's the future infinity, this scribe plus, and then the other is the past infinity at t equals minus infinity, which is scribe minus. So for the duration of this talk, I'm really going to be interested in scribe plus. So from now on, we can always think about talking about scribe plus, but the same discussion can also be performed for scribe minus. Okay, so that's just general pure de Sitter that we've seen thus far. But we'd also, when we're discussing waves and radiation, we want to have a more general class of spacetimes which in some sense look like de Sitter. but have more interesting properties than the maximal symmetry. And these are called asymptotically locally de Sitter spacetimes, which is a bit of a mouthful, but I'll try to explain how one categorizes these. So basically, we're looking at all solutions to the field equations with a positive cosmological constant, and in particular, all conformally compact solutions. And it was Starobinsky who first posed this idea that near this future infinity, near this scribe plus, one can always write the metric for these solutions in the following form. So it might look a bit weird, but really this is just a Taylor expansion in the coordinate rho, and rho equals 0 is the location of this future infinity at rho equals 0, so scribe plus. So I should also mention at this point, you can see there's this factor of 3 over lambda sitting out the front. And it's important this is a 1 over lambda term. Of course, when I said we want to look at a positive cosmological constant, your initial thought could be, well, in the universe, the cosmological constant is so small that we can just, say it's nearly 0. But as it turns out, the physics of gravitational waves and of asymptotically locally de Sitter spaces in general is discontinuous as lambda goes to 0, and so there's clearly a whole sort of new structure regardless of how small lambda is. But okay, that's sort of an aside. So I mentioned that there's this sort of Taylor series in the coordinate rho. Now I've highlighted 2 of the important terms in the series. So the first one is this G0, which one can think of as the representative of the conformal class of metrics. So these are all metrics related to G0 by a conformal factor, which is induced at scribe plus. And this is the guy that really determines the asymptotic classification of our spacetime. So if it's got the same conformal infinity as de Sitter, so if it's got the flat metric in there, then we say it's asymptotically de Sitter. But if it's got a more interesting structure and is not related to the flat metric by a conformal transformation, then we say it's asymptotically locally de Sitter. So that explains these terms, which may have seemed a bit unusual. So the next interesting term in this series is the G3, and between the G0 and the G3, these form complete Cauchy data for the solutions in the asymptotic region. And this may be also familiar to those who study ADS-CFT, as the G3 is related to, well, energy momentum tensor of the dual CFT in ADS-CFT. But here we'll still call it the energy momentum tensor, but it's strictly speaking the analytic continuation of what the energy momentum tensor was. So I'll sort of touch on this as we go through the talk. Right, okay, so that's sort of introduction to de Sitter spaces. So now I'd like to discuss the method that I'm going to use to try and compute charges and describe gravitational waves. Now, these are slightly technical slides, so try and bear with me, and hopefully sort of by the end of these, at least they'll have an understanding for what these kind of charges and fluxes I'm discussing are. So this is something called the covariant phase space formalism. This is a topic that's been kind of discussed sort of initially due to Witten and Cernkovich, and also by Ashtekar in the 80s, but I'm going to follow sort of the prescription discussed by Wald and others starting in the early 90s for how to construct charges. So this kind of procedure works for any diffeomorphism covariant theory with a D-form Lagrangian L of phi, where phi is the dynamical fields in the theory. So when we're just talking about these de Sitter spaces, L is always just going to be the Einstein-Hilbert action with a cosmological constant, and phi would just be the metric, but I'll keep the derivations generic for now. So when one varies this D form, one always finds the following expression. So there's 2 terms on the right-hand side. So the first one is just the equations of motion, and the second is an exact form, where the object getting hit by the exterior derivative is a d-1 form known as the pre-symplectic potential. So this may look totally weird at first sight, but really this is what one always does when you first learn about Lagrangian field theory in order to derive equations of motion, sort of take variations of the Lagrangian and extract the equations of motion, and sort of, at least when you're doing this for the first pass, throw away all the total derivative terms that you get by integration by parts. It turns out this theta term is actually the crucial object when constructing charges in spacetimes. So we'll keep it here for now. So, so once we have theta, there's then another step in this recipe where one defines another d-1 form, omega, which is defined as two anti-symmetrized variations of this theta that we've constructed from the Lagrangian. And omega is often referred to as the presymplectic current. Okay, so that's the second step. And then the third step in this procedure is to define the Hamiltonian or the charge. I'll use these kind of interchangeably in this talk. And one associates this both with a vector field psi in the spacetime and also a hypersurface C in the spacetime. And one does this defining the Hamiltonian basically as the integral of omega over this hypersurface C, where now one of the variations is replaced with the Lie derivative of the dynamical field in the direction of psi. There's sort of a game here to construct physically interesting charges of choosing both the hypersurface C to be something sensible and also the vector field psi to be a notion of asymmetry. So either a killing vector or an asymptotic killing vector. So this will come up as we're going through our de Sitter charges. But also notice that this notation here, this delta slash, really means that we don't always have existence of a Hamiltonian. So the right-hand side isn't always a total variation of something, f. So we really have to think about, okay, when does H exist? And it turns out that a necessary and sufficient condition is when the commutator of two variations acting on what would be H is 0. So this is quite clear that this is sort of a necessary condition, but the sufficient is also true. And when one puts this condition into form language, you find this corresponds to the interior contraction of psi with your presymplectic current integrated over the boundary of this hypersurface C being 0. And if this holds, then H exists, and we can use it to define conserved quantities, so charges. So if omega vanishes on a surface B, who's defined such that its boundary is the union of two slices of the spacetime, then the H associated with each slice is the same. So this is the idea of some invariant quantity. It doesn't change from one surface to the next. But then, of course, there's also the other case when H doesn't exist. And in this case, one needs an alternative method. Now, a proposal was made by Wald and Zupas in their 99 paper. And basically, the idea is that you just add back on the term that makes the integrability condition fail, where this now var theta is a symplectic potential for omega pulled back onto this surface B. And okay, so this immediately satisfies the existence property quite trivially, as one can check, but it's no longer conserved. Now the difference between two of these modified Hamiltonians sort of has a non-zero term on the right-hand side, which is really analogous physically to the flux passing through this surface B12. And remember I mentioned at the beginning of the talk that gravitational waves had this monotonically decreasing Bondi mass. What made it monotonically decreasing was precisely this flux passing through the conformal boundary of the spacetime. So, okay, that was all technical, but hopefully the pictures explain it a little better. So this method has been used extensively in both lambda 0 and negative spacetimes. So I mentioned Wald and Zupas. They adapted this method to look at asymptotic symmetries at scribe plus. So in this case, the charges are non-integrable, so one has to use this modified procedure in order to define them. And you find that, so for example here, one wants to look at the Hamiltonians associated with these two null slices, C1 and C2. And you find that due to gravitational radiation passing out through null infinity, generically there's no conservation, and one would find Bondi mass loss in this scenario. So that's an asymptotically flat space. Asymptotically anti-de Sitter space has also been studied, sort of in tandem with the ADS-CFT correspondence and techniques from something known as holographic renormalization. So in this case, one takes the psi that define the charges to be asymptotic conformal killing vectors. So they rescale the metric at the conformal boundary by a conformal factor. And in this case, one actually finds that the Hamiltonians do exist without the modification. So notice here, this is just a picture of quantities conserved as one goes from one time slice C1 to another time slice C2, and one doesn't have this outgoing flux through the portion of the conformal boundary B12. Okay, so that's sort of lightning review of a deep topic, but we're going to use this now to discuss charges in asymptotically locally de Sitter spacetimes. So what's the best?
I'm sorry. Can I make you a question? Sorry, Poole.
Yes, please do. Yeah, go ahead.
Could you go back 2 slides, please, when you introduce this pre-symplectic form?
I can try. Yeah. This one or one more?
No, one more, please.
Yeah.
Okay. So, is there any difference aside from the notation from your first equation between the traditional variation of a Lagrangian, in which you encounter these equations of motion plus boundary terms? I mean, it's just rewritten in a different way, but the equation is the same, right? Or am I missing something?
Yeah, it's really just the same. So this is, as I say, it looks weird, but it is the same thing. I guess the point of this, this generic method is that you haven't really chosen any coordinates at this point, right? You're just working on the covariant phase space. So you can use this to define charges corresponding to vectors that are not just tangent to the boundary, but also, those that aren't. So
okay, thank you. But the meaning of the equation is the same as one usually does with the Lagrangian.
Yeah, exactly. Yeah. So that's what I was trying to say. It's familiar, but it looks unusual. Yeah.
Okay, thank you very much.
Okay, you're welcome. Okay, so where was I? So I said we have to sort of think about the starting point for de Sitter. Now, I mentioned that there's a lot of work done when lambda 0, but actually the lambda negative case turns out to be a better starting point. So these are the anti-de Sitter spacetimes. And if one writes the asymptotic metric for any asymptotically locally anti-de Sitter spacetime, then basically it's a very similar form to the de Sitter metric. So this is the Fefman-Graham expansion. Again, probably more familiar to those who studied ADS-CFT, but really just the same thing as the de Sitter. And also, one sort of can use the past literature of the charges in such spacetimes, which was resolved in the paper I mentioned, this Papadimitriou and Skenderis, where they really showed that the charges that one obtains using holographic renormalization, so defining the Brown-York energy momentum tensor on a hypersurface at a finite distance in the spacetime, and performing the subtraction of covariant counterterms before removing the regulator, is equivalent to the charges that one finds from the covariant phase space. So there's already sort of a solid background here. The divergences are well behaved, and we want to sort of use this method to just start attacking de Sitter spacetimes. So how does one move from ADS to DS? Well, it's quite a simple procedure. It's just using basic analytic continuation, as outlined in this O2 paper. So really, when one wants to go from a Lorentzian to Lorentzian signature, you need to do a triple analytic continuation in the variables. So there's one between the two length scales of the two spaces, and there's also one between the ADS radial coordinate and the time in de Sitter, and then similarly between the time and radius the other way around. And so what do these really do when changing the analysis of the charges? Well, they change the causal picture from being a radial evolution in anti-de Sitter space. So these green slices are supposed to be constant radius moving out to infinity with time running along the boundary. So now a time evolution where as one moves forward in time, you're moving towards this space-like conformal boundary scribe plus, and now the R is just some coordinate that moves along the boundary direction. So this analytic continuation results in the picture of the following. So now we're looking at a portion of scribe plus, and we want to look at the charges associated with the slices C1 and C2, which we've obtained from analytically continuing the partial Cauchy surfaces in anti-de Sitter space. So these are now time-like surfaces in the de Sitter space. So it's a slightly strange setup to start with, but really just sort of turning the wheel of the covariant phase space formalism, computing, the theta omega, and then the capital omega before the Hamiltonians, one finds the following expression for the charges. So remember, this T is related to one of the expansion terms in the Starobinsky expansion, and the G0 is just the determinant of the metric that one gets at the conformal boundary. And we find again, which is expected from analytic continuation, that these charges are explicitly conserved. So the quantity associated with the surface C1 is the same as that associated with the surface C2. So we've got conserved charges in de Sitter, but we don't have anything that looks like flux. And therefore, at this point, we don't have anything that looks like gravitational radiation. So how do we put that in? Well, the idea is...
Could I ask a question?
Please do. Yeah.
So in here, you are continuing from anti-de Sitter to de Sitter, right?
Mm-hmm. Yeah.
So what if you, and in the case of anti-de Sitter, as you explained, there is no flux through the boundary, then in this de Sitter, there will be no flux.
Mm-hmm.
If you continue the other way around, so from de Sitter to anti-de Sitter, what plays the role of the flux that you had in de Sitter?
I think this is a good question, actually, one I've been sort of thinking about during this. So are you sort of suggesting that if one starts with a flux in a de Sitter,
right,
and then you analytically continue to the anti-de Sitter, there should be some analog flux in the anti-de Sitter?
Yeah.
Yeah, I think this is a good point. And I think, well, I think this picture that you can see now on the screen may be of interest to analytically continue back into anti-de Sitter in order to
Okay. I'll let you go. Sorry.
I think, yeah.
There are some questions by Andres and Nico, I think.
Yes, please go ahead.
So, Aaron, well, first, so you know that the Hamiltonian of in a asymptotically de Sitter spacetime is 0, right?
Yes, but I think this is a different sort of discussion, right? Because in that you're looking at a more traditional space-like slice, right? If I'm not mistaken.
Well, is that the thing is that the bulk term of the Hamiltonian is 0 because it's just the constraints, and then the boundary term is 0 because it's the space-like boundary, and since the space-like sections are S3s, the boundary of 3 is 0, right? So then everything is
yeah. So this but I think this does come from choosing. So these time-like slices, the C1, C2 here. I mean, now there is clearly, I mean, even if you don't think about the past piece, there's still a contribution at the conformal boundary from the future. But
so,
I agree.
And then this, my question is like this: you're integrating over this d2x. So what is this d2x?
I mean, it's basically a two-sphere.
Okay, so you pick a two-sphere inside the three-sphere.
Yeah, exactly.
Okay, and then this, okay, fine. And this psi I is an asymptotical killing vector.
Yeah, so it's actually an asymptotic conformal killing vector, but these are in one-to-one correspondence with the killing vectors. So.
Okay. Okay, good. Thank you.
Okay, you're welcome.
Okay, so let us postpone sorry, Nico, if you agree, let us postpone the questions for the end because we are running out of time. So Aaron can go ahead.
Sure.
Thank you.
Okay, so I guess the sort of questions built up to this. The idea is now, how can one add the flux? And well, the consideration is to now include past ends to the time-like slices as well as the future ends which anchor at the conformal boundary. So if one does this, now there's no longer a generic existence of these Hamiltonians. One has to use the Walden-Zupas procedure, and now you have a new conserved quantity in quotations here, because there's now a contribution from the past end. So this contribution is related to the momenta conjugate to the induced metric at the past hypersurface, this B12. And we can basically think of this as being closely related to the extrinsic curvature of that surface. And of course, as I said, now there's no longer existence of the traditional Hamiltonian. So there's a flux with the modified quantity, and this is given by the following expression. So this is the Lie derivative along the boundary or along the directions of B12 in the spacetime. Okay, so as I'm sort of running out of time, I'll now quickly give a couple of applications to exact solutions of these formulae. So the first one is to the Kerr Acetometric. So this described by two parameters, M and A. And as you can probably guess, these are analogous to mass and angular momentum. There's also an option to include a third nut parameter, which you won't do just for this discussion. So one first wants to recover formulae that you're somewhat more familiar with. And so one can start just by considering the hypersurfaces to have a vanishing past end. And so there's no flux coming in if one excludes the past end. And well, one uses the standard, or not quite standard, but uses Killing vectors of the Kerr de Sitter solution, and you can compute an analog of the angular momentum and the mass. But now I say mass, which is a bit unclear, because of course it's now associated with a vector, this vector here, which is explicitly space-like. And so it's really related to some spatially conserved quantity. So it needs a bit more interpretation than to say this is the mass. The second example and final one that I'd like to quickly mention is that of a locally DS example, which are those of Robinson-Troutman metrics. So these are solutions which admit a null geodesic congruence with no twist and shear, but they have a non-vanishing divergence. And they're interesting, particularly because they possess this Bondi mass type quantity, which one can obtain from the solutions, which is totally independent of the sign of the cosmological constant. So I've sort of stolen this figure from the this nice paper by Bichak and Podolsky about Robinson-Troutman de Sitter solutions. So these are expected to have radiation passing up towards Scribe plus. But one can explicitly look at the metric that gets induced at the conformal boundary of such spacetimes. As I mentioned, it's not conformally flat, so it's an asymptotically locally DS solution. But there are now no conformal Killing vectors of this metric. So it seems that we can't even construct the modified Hamiltonians using this symmetry group. There is an alternative to this, which is to relax the symmetries to just include all diffeomorphisms of Scri plus. And in that case, one finds, again, this slightly peculiar space-like Killing vector corresponds to the Bondi mass. But there's a caveat to this in that by expanding the symmetries to include all diffeomorphisms, one loses the well-posedness of the variational problem that you had with the asymptotic conformal Killings. And now flux passes through Scri plus instead of the interior hypersurface. Okay, so finally, I guess I'll just summarize and give some next steps. So we wanted to look at gravitational waves in asymptotically locally DS. A way to do this is to use the covariant phase space and analytically continue from ADS. Now we want to put fluxes in, so we consider this past boundary in the interior of the de Sitter space. But this is not quite the full story, so I've put some next steps here. So the first one is to fix some ambiguities in how one defines this additional term in order to put the flux in the past boundary. So there's a addition of this delta exact form, delta omega, which could change the theta. So one wants to fix this. We also want an explicit example where flux comes through the past surface and not through Scri plus. This is something that we're sort of looking for now. And finally, which is, I guess, kind of a big problem as well, is that all of this is in the near Scri plus region, But for a single observer in de Sitter, they're confined to something known as the static patch. So we have to try to extend these formulae, perhaps, in order to compute the fluxes through surfaces within the static patch. So I think that's everything. I've overrun a bit, but thank you very much for listening. And I'm happy to take any more questions.
Okay, thank you, Aaron. So I think we have time for 1 or 2 questions. So Nico Goensky, please go ahead.